So in this video, we're going to be looking at implicit differentiation. This is a type of differentiation that we deal with when we have a function that's not explicitly defined in terms of x. So all the functions that we've been working with up to this point have been y equals something that's been explicitly in terms of x. Now we're going to be looking at some functions that have the x and y's on either side of the equation. So we're going to have to figure out how we're going to deal with what happens if maybe I've got a y squared, or I have a term that has an xy, or in any way I can't solve the function explicitly for y equals something in terms of x. So that's what we use implicit differentiation for. This is a good example of an implicit differentiation problem, x squared plus y squared equals 12. We don't have this solved specifically for y, we've got a y squared involved. Solving this for y we could do, but we would end up with a plus or minus when we took the square root, and so we want to try and avoid that if we can. So the way that we're going to handle this is, remember that we're taking the derivative with respect to x. You have to pay attention to what variable you're giving respect to when you're doing implicit differentiation. If you're doing the function if you're differentiating with respect to x, then you can treat x the way that we've been treating it before. If you're, in this case, we're differentiating with respect to x, which means when we have the derivative of x with respect to x, we will get 1. When we have the derivative of y with respect to x, we'll get dy dx, or y prime. So I have to treat every other variable that's not an x, the variable that I'm giving respect to, like it's a function, and so the chain rule is going to come into play even when we don't think it looks like it should. Okay, so with this particular problem, we're going to differentiate each one of our terms one at a time. So we're going to start with differentiating 2x. That's a relatively simple power rule to differentiate. So the derivative of x squared is just going to be 2x. And then we get to our y squared term. This term is going to be a composite function. I have the function y that is being squared. So there's a function within a function that's going to require the chain rule. And so when I differentiate this, I'm going to start by using the power rule. The derivative of y squared is going to be 2y. But I have to multiply that times the derivative of y with respect to x. So I'm going to multiply that by dy dx. Now, I noted the notation here, dy dx here. Remember that notation really is, it doesn't matter. I can use y prime there if I want to simplify this problem a little bit, make the notation look a little bit easier. Either notation is fine. And then on the right-hand side, I've got the derivative of 12, which is going to be 0. The derivative of any constant is 0. So now I have this thing solved. I've taken the derivative for it. The calculus part of this is done now, but I also need to go back and solve this for dy dx. So what I'm going to do is I'm going to subtract both sides by 2x. That's going to leave me with 2y, and I'm going to go ahead and change my notation here to y prime. So I have 2y y prime equals negative 2x. I'm going to divide by 2y, and I get y prime equals negative 2 over 2x over 2y, which of course simplifies to negative x over y. There is my derivative for x squared plus y squared equals 12, solved for y prime. Okay, now notice that with this problem, my y, the original y function, is still involved in the derivative here. That happens quite a bit. So and that's okay, it's not a problem at all. The thing here is that I want to make sure that I've solved the equation for y prime. So let's take a look at one that may be a little bit more difficult to do. That one was a little more straightforward. Let's try something like y cubed minus 4y squared plus 2x equals 3y plus 5x squared. Okay? Now this one, obviously, we're not going to be able to solve this for y. We've got a y cubed term here. We've got a y squared term here. We've got a linear y here. We're not going to be able to solve this for y. So I'm going to differentiate this implicitly. I'm going to use y prime for my notation just to make this a little bit cleaner as we go through. I'm going to differentiate each term one at a time. So I'm going to start with y cubed. The derivative of y cubed, that's going to be a chain rule. And I get 3y squared times the derivative of y, or y prime. There's the derivative of y cubed. I'm going to go to the next term, negative 4y squared. Using the power rule, that's going to get me negative 8y. And again, I'm taking the derivative with respect to x, and so I'm going to find the derivative of the inside, or y prime again, plus the derivative of 2x, which is just going to be 2, times the derivative of x with respect to x, which is 1, so I don't need to see that. The next term I have 3y. The derivative of that is going to be 3 times the derivative of y, so it's going to have 3y prime. And then the last term I have plus 5x squared, which is 10x. So again, now I've got the calculus done. I've taken the derivative completely. All the calculus for this is done. The rest of this is just going to be algebra trying to find out what y prime is. So the way that I'm going to do that is I'm going to move everything that has a y prime to one side of the equation. I'm going to move everything else to the other side of the equation and try and isolate the y prime. So if this term has a y prime, I'll leave it. This term has a y prime, I'm going to leave it. I'm going to move the 2 to the other side. I'm going to move this 3y over here so that I have everything on the left-hand side of the equation has a y prime. Everything on the right-hand side of the equation does not. So when I do that, I'm going to get 3y squared times y prime minus 8y y prime. I'm moving the 3y over, so that's minus 3y prime equals 10x, and then I move the 2 over to the other side, so minus 2. Now notice that everything over here has a y prime. Since everything over there has a y prime, I can factor that y prime out. That's going to give me y prime times 3y squared minus 8y minus 3 equals 10x minus 2. And now that I have the y prime factored out, I can divide by whatever that's being multiplied by, and so my derivative for this is going to be y prime equals 10x minus 2 divided by 3y squared minus 8y minus 3. And there I have my derivative for this more complicated function. So a little bit more algebra involved there, but hopefully you see that the differentiation, the calculus part of it, was finished here. The rest of this was just algebra trying to isolate the y prime. Okay. Let's take a look at one more, because there's another situation that we might see come up here, and that's where we've got a term that has an xy in it. So let's say we had the function xy plus 3x equals 2y. Okay? This problem becomes a little bit more complicated because of the xy. I have to treat this like it's a product. I've got the function x multiplied times the function y. So that indicates to me that I'm going to have to use the product rule to differentiate this term right here. When I differentiate this using the product rule says to take the derivative of the first term, which will be 1, times the second function, which is y, plus the first function, which was x, times the derivative of the second function. The derivative of y with respect to x is y prime. So using the product rule, there's my derivative for xy. Now I can differentiate the next term. The derivative of 3x is just going to be 3. And moving over to the other side, the derivative of 2y is going to be 2 times y prime. Okay, so again, now I've got the calculus done here. It's a little bit more complicated just because I had the product rule involved, but now we're back to the point where we just have algebra to deal with. I'm going to again move everything that has a y prime to one side, everything that doesn't have a y prime to the other side. I think this time I'll just move this xy prime term to the other side. That's going to leave me with y plus 3 equals 2y prime minus xy prime. I'm going to factor out the y prime again. That's going to give me y plus 3 equals y prime times the quantity 2 minus x. And divide through by the 2 minus x to clean that up, and I find that y prime is equal to y plus 3 divided by 2 minus x, and there's my derivative for this function. Okay, so like I said, a little bit more complicated here because I have the xy term to deal with. But the idea here for implicit differentiation is just make sure you're paying attention to what variable you're giving respect to. I want to note here that if this had been differentiating with respect to t, maybe we're working with time, then each of these variables, x and y, are going to have to be treated like a function. And so this would have been the derivative of x here would have been dx dt. Okay, so you do have to pay very careful attention to what variable you're giving respect to when you're differentiating implicitly.